So, good afternoon, all of you. And I'm going to talk about you can say, complementary talk from our group. The more or less nuclear signature measurement with our accelerator setup, and little bit history of sodium iodide detector in the cold fusion aspects. So, if you look at the DD reactions, everyone knows that with the accelerator you have 3 known channels. But at thermal energy, it's very people try to you can speculate, but so far so not convincing measurement is available. For example, electron emission. But and they have put different kind of detectors, and preferably they have sodium iodide. Most of the time they have sodium iodide detector because of its versatility. Means you can measure the photons, neutron, gamma at the same time. So they put the sodium iodide detector, and this sodium iodide detector play a very important role in our field for declining the you can say the nuclear signature at the room temperature. Even some optimistic result were also there. So that's why you have to understand. Again, we try to revisit the sodium iodide spectra here, and they have other group also try to put liquid scintillator for neutron measurement, and for inside the setup they have used the CR39 as a charged particle detector. So before going in the deep of my analysis, I would like to give one kind of outline at the beginning of cold fusion history. So in 1989, after famous press conference, some controversial results were already reported regarding the heat excess by different group. So and Solomon was the colleague of Pons, and he was the particle physicist, and he asked Pons to allow his whole setup to measure everything. When I'm saying everything, he told Pons, we have very nice large volume sodium iodide detector, and this detector is capable to measure your neutron, proton, gamma, even if you have some unknown channel also from the internal conversion electron. So Pons at that time, they were quite occupied about their heat excess confirmation. But after several weeks, Pons allowed to Solomon to take whole electrolysis setup and coupled with the large volume sodium iodide detector. And this was the setup at the beginning. And the Pons, Solomon already discussed that this large volume sodium iodide detector is capable to measure even high energy Bremsstrahlung as well. Even the things what you are saying now, like internal pair creation 22.84 MeV, high energy electron can confirm via your Bremsstrahlung measurement. But at that time also he has some kind of idea. And here you can see the electrolysis setup of the Pons, and this is the large volume sodium iodide detector, which is shielded via the lead shielding to suppress the cosmic background. Okay, so what this spectra he has obtained with his setup, and upper panel you can see 2 figures. One is the inset, and other is the complete energy spectra. So in the inset, you can see the low energy spectra below the 3 MeV, and or you can see the natural background, thallium and the potassium, and higher energy region. He's tried to understand might be some high energy Bremsstrahlung as well. So he has subtracted this photon spectra with the background. Okay, and what he found that this background, if you look this background line, okay, it's almost at the 0 line, and at lower energy there is some fluctuation. But one thing I would like to mention here, this was not very long measurement, okay? And both were started to, not fight, but started to argue that okay, I didn't see your heat excess, I didn't see your nuclear signature, but the point was there is some missing link between them. What was the missing link? At the last of my talk, I will explain. So at the same time, nearly same time, M. Gai also tried to do the nuclear signature measurement with the medium size of sodium iodide detector, and with the different electrolysis setup. And he has tried to measure this neutron as well in coincidence with the plastic scintillator and sodium iodide detector. So here you can see the top view of the setup. And here this is the liquid scintillator and 2 sodium iodide detector. He has coupled. So what M. Gai observed? So M. Gai found that even in higher energy region, here you can see these 2 spectrum. One is the without BITO, means without making coincidence with the plastic scintillator to suppress the background. Okay, when you put the plastic scintillator to suppress the background, you can see the BITO effect, means the suppression of the background. And he has tried to look the higher energy and the PD gamma, this reaction as well. So, but he didn't find anything, and it was almost upper limit of the measurement. So, okay, so come to the recent works, and a little bit more higher energy, like not thermal energy. Recent works done by this Eric, and he has tried to measure this recoil energy of helium-4 using the DC glow discharge setup with the palladium electrolysis setup, and and he didn't observe helium-3 and triton. And one interesting thing I found that he is mentioning that he has put the nearly 20 micrometer thick aluminum foil. That's why he didn't see this didn't see any charged particle. But he is confirming this helium. This is the helium-4, and this might be the recoil energy of the gamma. So now I'm going to start our recent result. And if you remember at the beginning of our studies, 2.5 years back, I have presented in ICCF 24 the charge particle spectra, and where you use the thick silicon detectors, 1 mm and 2 mm, and the setup was it was very simple setup, and you have used the zirconium deuteride target. Here you can see zirconium deuteride target, and this is the beam, and the deuteride target was tilted at the 45 degree, and the beam we have taken the beam size of 7 into 12 mm, and we performed the experiment with the 5 to 20 kV with the different thickness of detectors, and you have put the different aluminum absorber. And parallelly, we try to understand the nuclear measurement with our Monte Carlo simulation, Giant 4 Monte Carlo simulation. And for example, if you have internal pair creation happens, then how it going to high energy, like 22.84 MeV high energy electron and positron, how it going to pass through 1 mm and 2 mm, 3 mm detector. So we performed firstly Giant 4 Monte Carlo simulation, and he found that if it pass through different thickness of detectors, you can see partial energy peak positions, not full energy peak position. Okay, and this was the Monte Carlo simulation. First, we started with the monoenergetic electron, and here you can see these different monoenergetic electron beam, for example, 500 eV, 1 MeV, 2 MeV, to 20 MeV. And interesting things, here you can see here the full energy peak for the 500 kV, 1 MeV also. But when you start to increase the energy, you can see the partial energy peak position is also start to increase. And as energy increases, the peak position, peak height is almost more clearly visible, and this full energy peak line is totally disappear. And this was the experimentally already confirmed with the earlier measurement as well by this author. So, so this is the final charge particle spectra with the different thickness of detector, where you can see this 2 mm thick detector and 46 micrometer aluminum foil in front of this detector. And here you can clearly see this bump, and along with the proton line. And this was very much reproducible with our giant pore Monte Carlo simulation. But in this figure, most important things, what you have observed, that if you look this 3 mm and 125 micrometer spectra, okay, with such a thickness of aluminum foil, only high energy particle can pass through, okay, because of the proton 3 MeV proton will be fully stopped. And you have seen that this might be the high energy electron. But what the energy correspond, it's very difficult to say experimentally, by looking only the partial energy peak, unless you don't measure the either full energy peak or some kind of other effect like sodium Bremsstrahlung. So with that purpose, we have used this large volume sodium iodide detector. And the size of detector was 20 centimeter diameter and 25 centimeter length. And it's nearly same size of Solomon used for this PF setup. If you remember at the beginning of my presentation, I mentioned that the size of detector was the 8 into 4 inch. And remember the spectra as well, because it's quite important to make a link. So you have placed this 37 centimeter from the target, and all the other experimental parameters for this measurement were the same as I have presented for the earlier charged particle spectra. So this was the setup. Okay, and I parallelly performed the Monte Carlo simulation as well. And in the Monte Carlo simulation, you can see this large volume sodium iodide detector. And it didn't not only put the large volume sodium iodide detector, it put the high purity germanium detector as well. And as we have mentioned, we are trying to look the internal pair creation. So there should be the high energy Bremsstrahlung as well as the annihilation peak effect as well. So before going into deep analysis of this measured spectra, I would like to give an example when neutron passes through the sodium iodide detector, how the response is going to be look like. So you can see here the calibration of the sodium iodide detector with the radioactive 252 californium source, neutron source. And here you can see this green with the 15 minutes exposure with the californium source. And this blue is the bare background without, there is the foreground, I can say. And another is the after the neutron radiation. This one is the neutron radiation effect. So there, because of the neutron lifetime, even this scintillator can measure some excess of the count. Okay, so finally we obtain our measured sodium iodide photon spectra. And so here you can see the blue one is our measured photon spectra at 10 keV. Why you have selected 10 keV first? Because of the neutron effect will be not so high. And we try to measure the background spectrum as well. And here again, I would like to mention that in our field, background is going to play key role to interpret a nuclear signature. So, and especially if you want to explain nuclear signature with accelerator, you have to be more cautious about this measurement because of the room temperature background measurement and accelerator background measurement has little bit difference. Okay, so but there is some common things, and this black one you can see here the beam background spectrum when beam is stopped at the Faraday cup. Red one correspond to the your background spectrum when accelerator is fully off, turned off. And parallelly, we try to look how much muonic contribution will be there. And we have taken the help of, again, Monte Carlo simulation, and we have corrected this efficiency with the existing same size of detectors measurement. So again, I would like to highlight few points. Before starting the understanding of measured sodium iodide photon spectra, you have to understand the accelerator-induced background, cosmic background, and electronic noise, which is coming from accelerator, and you can say your data acquisitions as well. And parallelly, you have to understand the reaction-induced effect. And for reaction-induced, you have to, when I'm saying reaction-induced, you have to very precisely, you have to estimate this neutron channel. Okay, and that can help you how much neutron has been emitted during that time when deuterium beam hit on the target. So then we separate the foreground and background events, estimate the neutron effect, as I mentioned earlier, and try to refine your neutron effect with the Monte Carlo simulation, and then then go for this weak effect in higher energy region. So, okay, so this, by following previously mentioned points in the slides, here I have presented this blue line, again this raw spectra, simply raw spectra without doing anything. And I started to understand this spectra with the help of Monte Carlo simulation and with some existing work. So here you can see this blue line is the raw spectra. Then this is the dotted, again, green one is the muonic contribution. And this red one is, as I already mentioned, this background. And this area of this color is correspond to the IPC-induced Bremsstrahlung, and orange color correspond to the neutron-induced photons. So if you include all these factors, you'll find that this black curve step size, and this black step size curve correspond to the sum over the channel of all these effects. So, but if you want to see this Bremsstrahlung very clearly, you have to subtract your spectra by including the previous components. And we have done that one. And what you found that this, what you found that this after subtraction, you can see here clearly this sodium iodide capture gamma peak, neutron capture gamma peak at the around 2 MeV, 3 MeV, 5 MeV, 6, 7, 6 MeV till nearly 6 MeV, and close to 6.5 MeV, you can see the sodium peak as well, and beyond 6 to 8 MeV, you can see the stainless steel effect, stainless steel effect, and this is the known as the neutron capture by the iron. So apart from this neutron capture effect, you can see some excess of the annihilation peak, and I will explain in later part of my slide. So, and most important things what I would like to mention here, when you have subtracted the background, we have sum over the channel, we have removed all those components, what you have found? We have found this high energy region, 10 to 22 MeV is well reproducible with the internal pair Bremsstrahlung produced by the internal pair creation. And, okay, so here I'd like to make one comment. In most of the time, with the cold fusion setup, people put the small detector, okay? If you look at this spectra, below 10 MeV, it's quite difficult to say anything, whether high energy component coming from electron or not. So so this is and another technical paper we are preparing about that, because of we have tried to put a small detector as well, like plastic scintillator and liquid scintillator and sodium iodide detector, and it was quite difficult for us to interpret the high energy effect. So finally, you have seen the axis of the annihilation line in this region for sodium iodide, and same things for the high purity germanium detector. And this, if you compare the axis of the annihilation peak, is 2-3 order of magnitude. And we have estimated, again, the branching ratio, just like the silicon detectors of different thickness. And you have found this branching ratio. If you compare with the silicon detectors, it's for this IPC versus neutron, it's double, because it is double count. It's going to be double with like E plus E minus. So it's going to be, it's going nearly double. And even for this annihilation peak as well, and for germanium as well. But one more thing I'd like to mention here. If you take the annihilation peak as a signature of the high energy Bremsstrahlung, high energy E plus E minus, an internal pair creation, only by looking the annihilation peak, we can say something, but it's not going to be very conclusive. So again, this is the Konrad has already presented this one about the electron-proton branching ratio, and here you can see this branching ratio measured for the different thickness of the silicon detectors, and clearly you can see this for effect of the different proton width with the different phase factor. There is a strong effect, and that room temperature, you can see this 2 order of magnitude difference, if you include the threshold resonance, proton width, and phase factor. But again, I would like to mention, still we are waiting for the confirmation of this kind of measurement with the other lab as well. So, a story so far. So you remember, I have already mentioned that what was the missing link in the earlier measurement of 90s and now. So missing link was the understanding of the high energy component. And if you look at the current Monte Carlo simulation and better background and understanding and better data acquisitions upgradation can help us to identify the signature of high energy component originated from internal pair creation. And so at the beginning, if you look the nuclear signature measurement in 1989, we have started, what was the problem? Problem was that we have started the observation with unknown and control mechanism. We thought that the mechanism was controlled, means you can do some kind of control, but unknown signature. But we have then we went for the little bit more higher energy, like a nuclear signature at gas discharge setup in close nearly in, early of this century. And but our idea is, before going to the room temperature measurement, let us try to understand the known mechanism with the help of known mechanism and much more control mechanism, and then implement to that understanding to the gas discharge setup, and then go to the room temperature. So, a story so far. We have presented the first indication of electron in ICCF 24 and ICCF 25, and we have and with the help of the charged particle spectra. And here again presented the Bremsstrahlung and annihilation signature in DD reaction. So if you combine 2.5 years understanding about DD reaction from our group, you can say that we have seen the high energy electron. And upcoming, our plan is like we'll go for the room temperature measurement, and we need some help from our consortium to look the reproducible heat module before putting the nuclear setup. Thank you.
Yes, Dimitar, yes, question.
You're supposed to answer on the question about definition of the electron effective mass. I'm asking this question not because actually I have to ask, but because actually you are third presenter of the achievements of your group today. And maybe you have more results. It is a very essential part. This matter actually correlates with your actual presentation, with presentation of Matthew Wallet, Konrad Chevsky, and Natalia. That's why I'm asking this question again.
Okay, though I am not expert of the solid state physics mechanism, yes, but I can try something from my side, okay? So effective electron mass it's very difficult, for me it's very difficult to correlate how it can affect the fusion process, honestly. So
thank you very much for your response. Thank you very much. No, it's good response, but in any case, it doesn't correlate to the density functional theory and the corresponding electron band structure used calculated by density functional theory. Okay, and something else, the collective behavior of the electrons, it's true. In fact, actually, the screening is subjective if it is product of collective behavior. However, this electron must be localized, not somewhere in the space or in the crystal lattice. It's my opinion. Thank you.
All right, thank you very much. If there are no further questions, yes, let's go.
Yes, I have.
Okay, thank you very much. There was one other question. I'm sorry. There was one other question. Kasagi-san, please ask your question. Yes, sir.
Yeah. Yeah, you are suggesting that from the real cold fusion experiment, like ours or some else, I mean that from the just putting the temperature, let's say 1000 K or so, then we should have your electron positron annihilation effect. You are suggesting that, but we did carefully search for that kind of things, but right now I didn't see any evidence. We have enhanced, for example, 511 peak. The similar. We did a very careful experiment with the NEDO project just 8 years ago. So.
Okay, so I would like to make a few comments about that. So first of all, if you look the annihilation peak with respect to what? So you have subtracted the background, right?
Well,
with respect to the background.
Yes.
Excess of the background.
We measure the background very long time, and we measure the foreground for a very long time also, and subtract. Just compare these two, and then we didn't see any evidence. That's my comment. Okay.
So here we have seen this effect with the. We have confirmed this one with the simulation as well, and we have put this IPC, internal pair creation E plus E minus, in the Monte HP germanium detectors, and you must see.
I'm thinking that the the mechanism is different. It might be different of mechanism. You are making the very sharp resonance by beam impinging experiment. We are going to the other ways. Maybe the different mechanism. We didn't get to that resonance.
Conrad, would you like to talk about that?
You have seen that this effect is very weak. So we measured at 10 kV, and at this plateau level we have seen there was 6 orders of magnitude below. So it means that cold fusion, in your case, if you measure milliwatt, yeah, the point is, I think, at least I believe, that the effect is so weak you cannot see it directly. You should use coincidence two detectors. Okay, you should use coincidence two detectors, and then you can reduce the background strongly, and then you can see this annihilation. I hope, yeah. We will want to do the same. So
even the size of detector also matters.
What we want to do is to use two detectors in coincidence.
Our conclusion that time is if there's a within a 3 sigma uncertainty, we have no difference, and then the reaction, such kind of things. I mean, creation of pair creation.
But the problem is something else. If you produce positrons, they should annihilate somewhere. It is for that you should use Jant for simulation. There's not every electron will not annihilate.
Yeah,
so there's
right.
yeah. Okay. Yeah. There's a point. There is something that's not so easy. We tried. Rakesh tried. To do it better. Yeah. So.
All right, I'd like to announce the next paper. It is...
Someone...
No, let's go. Okay.
Pardon? Oh, there was one more question. Doc, do you wish time for one more?
It's up to you. But,
As long as you gentlemen don't, ladies and gentlemen, don't mind that we will be a little late for dinner, then we're fine. We have a question. Go ahead, yes, sir.
Okay.
Yes, sir.
Is he still available for questions?
Yes.
Yes or no?
If you could come up for one more
a short
question.
one.
I'm sorry.
Okay, my question is the following. If I got you right, your presentation was based, or the measurements were based on 10 kilo electron volts, the order of 10 kilo electron volts, deuterium beams. Now, I'm very confused with this, because in my opinion, that is hot fusion and not cold fusion or LENR. Can you explain why you think this is LENR? I'm completely confused with your presentation. Sorry about that.
Even 10 kV is LNR. It's not, it's low energy. And if you look at the discharge setup, it's 500 EV, below 500 volt. You can go for, you can say this thermal energy and cold fusion stuff. But so far, so it's not cold fusion. It's accelerator-induced effect, I can say. But we are planning to do this measurement at very low energy, below, you can say, order of EV, few hundred EV, and then you can say that might be the cold fusion. So in future, you have planned some experiment in the coincidence with the different delta telescope. But so far, so this is the high energy stuffs.